Hi, my name is Philip Bello. I'm a Senior Product Manager here at Insertion Company. Today we're going to show how you can use the Microwave Site Master S820E to easily measure the insertion loss of various building materials that you might find. In particular, our focus is on the FR2 bands for 5G, since these are the wavelengths or the frequencies that getting signal penetration is a problem, and we all want to have that strong signal indoors. So what we have here is a variety of materials that we're going to test today. We have some drywall, or otherwise known as gypsum. We have a piece of a typical cubicle building material for when you're in office environments and they build cubes. We have a piece of that. We have a piece of wood. We have two different types of thermal pane windows. We have a couple of pieces of foam that might be used as insulation, and we have some fiberglass insulation. And what we're doing here, we basically have two horn antennas set up on tripods, and again, this is something that you would set up in the field, so fairly easy to set up. It doesn't have to be super perfect. It's not doing materials characterization, which you would probably do in an anechoic chamber. This is just a way to quickly determine whether your material is going to block that signal or whether it's going to allow it to pass through. And on the table we have the Microwave Site Master S820E, the standard configuration. There are no options required for this measurement. We're simply doing a transmission 2-port with a transmission 2-port calibration, which has already been applied. And for this experiment today, we're sweeping from 27.5 gigahertz to 28.5 gigahertz, which is the 28 gigahertz band, which is fairly common in most regions. The Microwave Site Master can support anything up to 40 gigahertz, so the majority of FR2 bands are supported with this product. So let's get started. The first thing we'll do is we'll measure this piece of drywall, and I'll just put it in between, and we can see that very little attenuation from the drywall, so this is actually good news. Next, we'll take this piece of cubicle building material, put it in between, and we see that we've completely lost our signal with this material, which tells me that internally this material has some kind of metal. It's probably aluminum, and it's completely blocking our signal, so we wouldn't be getting very much through that. Here we have a piece of wood. It's approximately 3/4 of an inch thick, or 15 millimeters. And again, we have about maybe 4 dB of loss only, so that's pretty reasonable. I'm going to go to the foam. This is just a half-inch piece of foam that you'll find, various places. It's not really used for building, but it was interesting to show that the foam itself, open cell foam, really has no effect on the signal whatsoever. We'll get to the fiberglass insulation. So this is obviously commonly used in exterior walls to insulate buildings, and we're using about 8 inches of thickness. And again, absolutely no impact on the signal. Next, we have a representation of a thermal pane window, which you'll find in residences and commercial buildings. This one's made with some fairly thin glass. It's just two pieces put together. It's not an actual thermal pane, but it represents what a thermal pane would be. And here we can see, we've got some loss, 3 or 4 dB depending. It's not significant. The last item we're going to test is a different type of thermal pane window. This is one of the energy efficient thermal pane windows. It has what they call low E glass in it. And we put this in between, and suddenly we've lost over 40 dB of our signal. So while this is an energy efficient window and it may be nice for saving heat or cooling, it's absolutely detrimental to the millimeter wave frequencies. For more information, there's an application note you can find at our website, www.aritsu.com, and thanks for watching.